So commonly observed in larger molecules. So I'll write commonly observed transitions in, quote, larger molecules. And you can see here I've got acetone as my large molecule example. Okay, so pi to pi star and in to pi star transitions are very common in UV-Vis spectra in large molecules. In fact, I would wager that's probably the only type of transition you've seen in your experience with UV-Vis. Okay, so typically you need to have some degree of conjugation or even just some very simple pi bonding system. So you can see here with my example using acetone, very simple pi system, just one carbonyl, okay? And so recall the pi state is the bonding orbital, right? And then way at the top up here is pi star. So I'll redraw this diagram like this here, where we're not even focused on the sigma bonds. I just want to focus on the pi and the pi star, the bonding and the anti-bonding, okay? So that's a very common transition to see in absorption spectra, pi to pi star. And typically that occurs way down in the UV, okay? So pi to pi star is almost always UV. And you can see for acetone, that occurs at 195 nanometers. So that's a very high energy transition, which makes sense when you think about these MO diagrams, right? Well, then what is an N to pi star transition? Well, an N, represents a non-bonding orbital. So typically that's coming from a lone pair, okay? So our N to pi star, as you can tell from this diagram, will occur at a lower energy. And you can see for acetone, N to pi star occurs at 274 nanometer. And here we're seeing those diagrams of the molecules. Oh, excuse me. So what ends up happening, so there's something really interesting that happens with pi to pi star and N to pi star. So you notice the pi to pi star is occurring at a much higher intensity than N to pi star. And that's because pi to pi star transitions are allowed and N to pi star transitions are forbidden. And that's forbidden due to the conservation of angular momentum. So it's a spin forbidden transition. And that's related to the fact that if you look at the pi bonding structure showing constructive overlap of p orbitals here, and then the anti-bonding shows destructive overlap, okay? The change in angular momentum from pi to pi star can be conserved with the photon. And I'm not going to get into the quantum numbers, I'm not going to get into the details, but it has everything to do with the geometry of the pi bond and the pi star bond, okay? So now the non-bonding electrons, and in this case in acetone, we can see those are the lone pairs over oxygen. Those are in the same plane as the CR bonds, which do not allow conservation of angular momentum to transition from these non-bonding electrons to the pi star, okay? So that should be forbidden. But you can see that it's not forbidden, it's actually observed. And the reason why it's observed is because acetone, like all other molecules, is kind of floppy. It can distort, it can rotate, it can vibrate. The rotation only in the gas phase, right? But certainly the vibrations such as the symmetric stretching, the asymmetric stretching, and the bending motion particularly, okay, will put those non-bonding electrons out of plane of the CR bonds and into the plane of the pi star. And so that means occasionally there is an orientation of this molecule that will allow a transition from the N, non-bonding orbital to the pi star anti-bonding level, okay? And that's why you see it occurring at very low intensity. So now what happens as the molecules get bigger? Well, It's a particle in the box phenomenon, right? So as molecules get bigger, I'm sorry, my handwriting is really failing here at the end of the semester. So as molecules get bigger, these transitions will shift to longer wavelengths, okay? So for example, nitrate, NO3 minus, has a really nice pi to pi star and N to pi star UV-Vis spectra. And it looks almost identical to this acetone spectra, although it's just shifted down by about 100 nanometers because nitrate is just a little bit bigger than acetone, okay? So this is pretty cool. So if you've ever seen a UV-Vis spectra where you have really, really high absorbance in the UV, and then you get a secondary peak, perhaps into the visible, but also still maybe in the nearer UV, you know that that's pi to pi star for the big peak and N to pi star for the little peak. Okay, so this is very common in molecules. Let's see, the final thing, I've got this little Jablonski diagram. I know you guys have done these before in instrumental. I know not all of you have taken instrumental. So I'll just kind of briefly introduce these Jablonski diagrams as a way of really organizing all the photophysical, radiative, and non-radiative transitions. And so what I want you to do on your own, maybe in good preparation for the spec super quiz, see if you can identify what all of these transitions are, and I'll label what they are in the next video. Okay, folks, that's all I got for this video. Our very last video will be all about lasers. Hasta!